You've probably never heard of it, but I guarantee you've used it dozens of times just today. It's this tiny, incredibly powerful chip that's been the secret heartbeat of our electronic world for over half a century. So today, we're going to pull back the curtain on one of the most successful integrated circuits ever made, the 555 timer. So, have you ever stopped to wonder what actually makes a kitchen timer ding at just the right moment? Or how does a car's turn signal know how to blink with that perfect, steady rhythm? It might feel like magic, but behind these everyday things is some seriously clever engineering. And yeah, more often than not, the secret ingredient is this little guy right here, the 555 timer. For over 50 years, this humble 8-pin chip has been the absolute workhorse for anything that needs precise electronic timing. Why? Because it's cheap, it's reliable, and it is every wet. So what is this thing, really? Well, the official definition calls it a monolithic timing circuit. Okay, let's break that down. Monolithic just means it's all made from a single piece of silicon. And its job? Well, it's a master of time, and it's really, really good at two things. Either creating one single precise delay or generating a continuous, nonstop beat. And that right there brings us to the 555's two very distinct personalities. What's so incredible is that you can get it to switch between these two completely different behaviors just by changing a couple of simple external parts you connect to it. So on one hand, you've got what's called monostable mode. Just think of it as a one-shot timer. You hit a button, it runs for a set amount of time, and then it stops. That's it. But on the other hand, you've got astable mode, which is more like a metronome. It doesn't need to be told to start, it just keeps pulsing away, creating this continuous, never-ending beat. All right, let's dive a little deeper into that first mode, the monostable, or, as we like to call it, the one-shot timer. This is the 555 at its most basic and direct. Honestly, the best way to think about this is a toaster, right? You push the lever down, that's your trigger, and it runs for a specific amount of time to toast your bread. When that time is up, it pops up and just waits patiently for you to trigger it again. It only ever does one cycle at a time. So how does it work? It's just beautifully simple. First, it gets a trigger signal. You can think of this as just a quick dip in voltage that tells it, okay, go. Then the magic happens. The length of that time delay is set by just two external parts, one resistor and one capacitor. And once that time is up, the output just shuts off and waits for the next trigger. And here's the coolest part. The math is just so elegant. This simple formula is all you need to know. The time delay is just 1.1 times the value of your resistor times the value of your capacitor. That's it. By just swapping out those two little components, you can create a delay for, a split-second camera flash or a timer that runs for hours. Okay, so that's the one-shot timer. But what if you don't want it to stop? What if you want a continuous pulse? Well, let's switch over to our second mode and see how one tiny change gives us a completely different result. This is astable mode, and our new analogy here is a metronome. See, this one doesn't need a trigger at all. You just power it up, and it starts producing a steady, continuous, free-running beat. It's like a clock's tick-tock. It just goes and goes. So what's the secret to unlocking this new mode? It's almost ridiculously simple. All you do is add a second resistor, called RB, to the circuit. So now, instead of just a resistor and a capacitor, the rhythm is controlled by two resistors, RA and RB, and our trusty capacitor, C. That's all it takes. That one extra part completely changes the chip's behavior from a timer to an oscillator. And just like before, there's a simple, predictable formula that governs everything. This equation lets you figure out the frequency, that's how many pulses per second you'll get, just based on the values of those three little parts. This is basically the recipe for everything from a blinking LED on a toy to the sound generation in a simple synthesizer. So what's actually going on inside the chip to make all this happen? Well, it's surprisingly simple. The whole show is basically run by two main parts. A pair of comparators, which act like tiny voltage guards, and a flip-flop, which is just a simple memory switch that remembers if it's on or off. This incredibly elegant internal design is really the core of the 555's genius. Okay, so we know how it works, but why has this thing been so unbelievably popular for half a century? Let's do a quick run-through of some of its key superpowers. First off, its output is surprisingly beefy. It can push or pull up to 200 milliamps of current. What does that mean in plain English? It means you can hook things like LEDs, electromagnets, and relays, or even small speakers right up to the chip itself. No extra power boosters needed. It's got the muscle to do it on its own. It's also really, really fast. We're talking a maximum operating frequency of over 500 kilohertz. That means it can create over 500,000 pulses every single second. That kind of speed makes it useful for a huge range of jobs, from creating audio tones to generating digital clock signals. And that brings us to its insane versatility. This one little chip can create pulses that last for just a few millionths of a second, or, with the right parts, it can be a stable timer that runs for hours and hours. That's an amazing dynamic range from one single, simple component. And get this, it does all of this with incredible stability. Its timing barely changes even when the temperature swings wildly. We're talking a drift of just 0.005% per degree Celsius. As you can see on this chart, whether it's freezing cold or boiling hot, that timing stays rock solid, which is absolutely critical for any kind of reliable electronics. So, when you put it all together, the power, the speed, the huge range, the stability, what you get is a chip that's a true jack of all trades for anything related to time. It gets used for precision timers, pulse generators, circuits that do things in a sequence, time delays, and even for controlling the speed of motors. So, the real takeaway here is that a simple, robust, and amazingly versatile design from the early 1970s is still one of the most useful electronic components in the entire world.